Hello and welcome to the last of the lectures in this week under the course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. During the course of this week, we have seen one particular generalization of conjunctions, namely that of the triangular norm or T-norm for short. We have seen the different kinds of continuity that we could relate to with respect to a T-norm. We also saw some algebraic aspects of T-norms, both at the elemental level and also at the level of a function, and offered a few classifications on the set of T-norms. We also saw three major ways of constructing T-norms and how they led to useful and insightful representations. In this lecture, we will look at obtaining a complement from a T-norm and also discuss fuzzy disjunctions. Again, one particular generalization of a fuzzy disjunction as a T-conorm, which can also be seen as an end dual of a T-norm. We have seen what a complemented lattice is. It's a bounded lattice in which every element has a complement. Complement of an element means given an A, B is said to be its complement if A join B is 1 and A mate B is 0. Then we said we could look at this operation itself as a function from L to L. That means negation of A is B if and only if A join B is 1 and A mate B is 0. Unfortunately, on the set of on the unit interval, we could not obtain a complemented lattice with the operations that we have seen. We have also seen that we could introduce another operation called the pseudo-complement. Once again, we need a bounded lattice L. We say an element A star is a pseudo-complement of A if these two properties are valid. And when you compare the complement to the pseudo-complement, we see it satisfies the first of the two conditions. The pseudo-complement satisfies first of the two conditions that you expect of a complement. And if you recall, the second condition is what in some sense we have introduced as the Stone's identity. What does pseudo-complement of an A stand for? In plain English, it says A star is the largest element such that A mate A star is 0. Now, let's try to generalize this definition of a pseudo-complement to our setting, where we look at L as 0, 1 and meet as the T-norm. So given an A from open 0, 1, because anyway we know 0 maps to 1 and 1 maps to 0 under complementation, take any A from the open interval 0, 1. For a fixed T, we could perhaps define A T star, the pseudo-complement of A with respect to T, as follows. So take a T such that T of AT is 0 and we are looking at the largest such T. So that is why the supremum comes into picture. So we could look at supremum of this set, the set which consists of all those T such that T of AT is 0. Now if you look at this particular pseudo-complement that we have obtained to make this structure a pseudo-complemented distributive lattice, it is clear that this A star actually has been obtained by the formula above when T was the corresponding minimum T-norm. Let's look at this. The definition for A T star was given like this. Supremum of T with the T of A comma T is equal to 0. Now look at A coming from open 0, 1 and T is the minimum T. Now if you wonder what is this set of minimum of A comma T is equal to 0. Now this set consists only of 0, because if you want to take minimum of A comma something to be 0, if A is not 0, it is coming from open interval 0, 1, so then T has to be 0. So now if you apply supremum on this set, the supremum is also 0. Now this is a set 0, this is just an element 0. So you see that this is exactly what we have got in this definition. So now, taking cue from this, let's define a natural negation of a T-norm. We'll denote it by nt, the n coming from the T-norm T, as a function from 0, 1 to 0, 1. As we saw, complementation as a function on it. Let us define it like this. Supremum over all those t such that t of xt is equal to 0. Let's look at what could be the natural negations for the typical 5 examples of T-norms that we have been considering. We have just constructed that for the Tm, the minimum T-norm, this is the natural negation for it. How would it look like for Tp? Once again, A comes from 0, 1 and T is the product T-norm. And you will see set of all T such that A dot T is equal to 0. Now if A is not 0, then T has to be 0. So then this set is 0, which means its supremum is also 0. So, which means we get essentially the same natural negation also for the product T-norm. Is it different for the Lukasiewicz T-norm? Let's look at it. Once again, A comes from 0, 1 and T of xy is a Lukasiewicz T-norm, which is maximum of 0, A x plus y minus 1. So now if you take a T so that TLK of AT, if you want this to be 0, look at this, maximum of 0, A plus T minus 1. Now you want this to be 0. That means A plus T minus 1 is 0. When can this happen? It can happen only if T is less than or equal to 1 minus A. If T is equal to 1 minus A, it is 0. If T is any number less than 1 minus A, it is again 0 because of monotonicity of the T-norm. So the supremum of this will actually be, so if you look at this, T such that T of A, T is equal to 0. This set will consist of 0 is possible one, 1 minus A inclusive of it. So if you're looking at supremum of this, is 1 minus A. So now this happens for every element A from 0, 1. Thus, we get that the natural negation obtained from Lukasiewicz T-norm is in fact 1 minus x. We could do the same for the other T-norms also, but let's have a geometric perspective of this. Now, this is the Lukasiewicz T-norm, the graph of it. And what is the natural negation? It is the supremum of all those t such that t of xt is 0. Now, what does it say? It says for a given x, you find all those t such that t of xt is 0. So somehow it seems to be talking about the 0 region of the T-norm. So essentially what lies on the floor on the xy plane. Now if you look at this Lukasiewicz T-norm, let's look at the boundary of the 0 region, which is now marked in blue. Remember, it is a continuous T-norm, so the boundary belongs to the floor as well to the rising graph, rising surface. But now let's pick one element. Let's say 0.2. Now, all we are seeing is what if A is 0.2, we are looking at what is that T, what are all those T such that T of TLK of 0.2, T is 0. Now, that means we are looking at all those points on this yellow line. Because for every point on the yellow line, every T on this yellow line, T of TLK of 0.2, T is 0. So the supremum, if you are looking for it, essentially it says how far can you walk? That means we can walk only till the edge of this 0 region. So essentially what you are characterizing is the boundary of the T-norm. Same way, if you take 0.4, how far can you walk? We know that we can walk only till 0.6. Just as in this case, when A was 0.2, you could walk only till 0.8. The moment it is greater than 0.8, then T of 0.2, T is no more 0. It's not 0. So that's how you actually get the natural negation of the Lukasiewicz T-norm to be 1 minus x. Let's explore this for a few more things. In hindsight, or in the light of what we have discussed, if you look at the minimum T-norm, where is it 0? Only on this boundary. That means when x is not 0, it has to be 0, and it is 0 here. And when x is 0, of course, it can go till 1. So is the case with the product T-norm, because their 0 regions are only on the boundary where x is 0 or y is 0. Now consider the nilpotent minimum. Now clearly you have this 0 region, part that is on the floor and rest of it actually above. Now you see that this black line tells you the boundary belongs to the floor, and this dotted black line tells you the boundary doesn't belong to the surface that's above the floor. So once again, it is much like the Lukasiewicz T-norm setting. If you start with any x, you can only go up to 1 minus x. That's the boundary of the 0 region. So far we have considered left continuous T-norms. That means T-norms or continuous T-norms for whom the boundary belong to the 0 region. Now let's consider some T-norms for whom the boundary of the 0 region actually does not belong. You look at this, on the open 0.5 square is where it is 0. So that means the blue line is the boundary of the 0 region but does not belong to the 0 region. That's why it is shown as a dotted line. However, if you take a point and walk, start from point 2, how far can you go? You can go almost till 0.5. The moment you touch 0.5, the minimum operation applies on it. But you can walk almost till 0.5. So essentially, if you look at set of all t such that TTB of 0.2 comma t is equal to 0, you see that this set is, of course, 0 belongs 0 comma 0.5 open. The moment you put 0.5, you are no more in this region, you fall in this domain, which means it becomes minimum of 0.5 comma 0.2, which is 0.2, and that's what you see here. Now this is the set, and you want to apply supremum of this. From what we have seen earlier, we know the supremum of this set is in fact 0.5. And you see that from 0 to open 0.5, you can walk for each one of those points, you can walk actually till 0.5. So when you see it like this, it's easy to construct the natural negation from the graph of the function itself, if you know it. So essentially, it is the boundary of the 0 region. For 0 it is 1, between 0 and 0.5 open it is 0.5, and from 0.5 to 1 closed, it is actually 0. Now let's look at this particular T-norm, which we have seen as neither left continuous nor border continuous, because at 1 it is not continuous. So now, if you take any point here, 0.7, it is clear you can only walk till this point, which is in our case 0.5. You see that once again these blue lines are dashed or dotted, which means the boundary does not belong to the floor of this graph, doesn't belong to the 0 region. Similarly, if you start here at 0.2, you can almost walk till 1, which means this is the natural negation of this particular T-norm. So between 0 and open 0.5, you can almost walk till 1, but 1 is not there, remember, because at 1 it has to be the identity, so it climbs up here. But till 1 you could walk. Similarly, you can, for say 0.7, you could walk till 0.5, almost till 0.5, but not touch 0.5. So you see that the natural negation somehow is capturing the boundary of the 0 region. And for TD, it is very clear now that everywhere it is 1 except at 1 which is 0. Well, from this, you could also talk about negations in general, not really being obtained from T-norm. What's a fuzzy negation? So this is just a complementation for us. So that means a negation as a function from 0, 1 to 0, 1. What do we expect of it? The boundary conditions, n of 0 is 1, n of 1 is 0, and order reversing function. Means when x is less than or equal to y, it should imply n of x is greater than or equal to n of y. Of course, we can ask for other some interesting or useful desirable properties, that of involution. We say negation is involutive, like in the case of classical complementation, n of x is x. And then n composed of itself gives you identity. We could also ask for a few other interesting properties, that of continuity and of strict decreasingness. That means when x is not equal to y, n of x is not equal to n of y. It is interesting to see whether these three properties that we have added. Note that this is the standard definition of a negation. All we want is boundary property and this monotonicity. Monotonicity in the sense of decreasingness. Everything else is what we would like it to have, desirable property. So let's look at the desirable properties. How are they related? For example, if you look at the natural negation that you get from product or minimum or the drastic T-norm, you will see that they are neither involutive nor continuous nor are they strict, because they are constant in most of the cases, either 0 or 1. If you look at this particular function 1 minus x squared, it is not an involution. Clearly n of x is not x. This can be seen. N of x is 1 minus x squared. N of x is 1 minus x squared. You will see that this is actually x squared and not equal to x. So this is not involutive. Of course, it is continuous, and we see that it is strictly decreasing. If you look at this function, it shows, so in fact the graph of this function would look something like this. So up to 1 by 3, it falls from here to here. Then between 1 by 3 and 2 by 3, it is 0.5, and then it comes down to 0. So you can see here, it is continuous, but not strictly decreasing, and it is not also involutive. Now, what about other options? If you see, you cannot find any example such that it is only strict and not continuous or involutive. It is involutive but neither continuous nor strict, and other such options. Why is it so? We will see that presently. One last example, if you look at root 1 minus x squared, or the natural, usual classical negation of 1 minus x, it is involutive, continuous, and strict. Now let's try to answer why we were not able to find examples in these 4 rows. If you start with an involution, it is n of x is x, we can also show that such a negation will also be strict. That means it will also be strictly decreasing. It is actually quite simple to see. What do we have? We need to show involution implies strictness. So involution means n of x is equal to x. So let's for the moment assume that x is not equal to y, but it is not 1 to 1. That means n of x is equal to n of y. But this means if I apply n once more, n is a function, so n of x should be equal to n of y. But because it is involutive, n of x is x, this is y, and it says x is equal to y, contrary to our assumption. So that means essentially we are saying if n of x is n of y, then x has to be equal to y. So clearly, if it is involutive, you know that it is also strict. But it can also be proven, because of this monotonicity, strictly decreasing, and because of the boundary condition, that such a negation has to be continuous. The proof is not very difficult, but it can be seen. We can work this out. If the context warrants, we will look into similar such proofs a little later on. So involution implies strictness, and strictness implies continuity of the negation. Well, so much for the complementation operation. There is a lot more to it. We could talk about fixed points, equilibrium points, and different kinds of negations. But as I said, if the context warrants, later on we will look at such special types of negations or special properties of negations. For the moment, let's look at fuzzy disjunction. One particular generalization of fuzzy disjunction is called a T-conorm, triangular conorm. It's a function, binary function on 0, 1, which is associative, commutative, monotonic increasing, and 0 is the identity for it. Unlike the T-norm, where 1 was the identity, for a T-conorm, 0 is the identity. So you see that almost everything is same. Looks like only the identities got switched, swapped from 0 to 1, 1 to 0. There 0 was annihilator. Here 0 is the identity. Of course, it can be shown that 1 is annihilator here. Now the question is, can we relate S and T through this negation? What if we take a T norm T and define S of x as n of T of nx, ny? Will this become a T-conorm? Now let's look at it. What do we need for it? We need this to be commutative, S is commutative, as is clear because T is commutative. Is it monotonic? Note that as X increases, N decreases. As N decreases, T in the first variable decreases. But N is a negation, so again it increases. So which means it is monotonic. If you put 0 here, then this is essentially T of N of 0, which is 1. And what we get is, for 0 to be the identity element, we want that N of T of N of 0, N of y, this is equal to N of T of 1, 1. This is N of y. So now if you want this to be y, it is clear that this implies N has to be involution. Now what about associativity? Yes, if N is an involution, then you can easily see that it will also be associative, much like in the case of taking the additive generator F circle F inverse. The N circle N will be identity. So if you use an involutive negation, then every T-norm gives rise to a T-conorm, which is called the dual T-conorm of the T-norm T. Let's look at some examples with respect to 1 minus x as a negation. It's easier to plot and easier to see the relationships. So if you have minimum, the 1 minus x dual of minimum is the maximum. So graph of minimum looks like this, the maximum almost the inverted one. In the case of product, this is the corresponding dual T-conorm x plus y minus xy. The graph of product is on the left and almost an inverted dual of that is the T-conorm, which is dual of the product T-norm. For the Lukasiewicz T-norm, this is the corresponding Lukasiewicz T-conorm. What is interesting is for the nilpotent minimum, you see here, for the nilpotent minimum, the boundary of the zero region belongs to itself. So this is in that sense, for every increasing sequence, the limit will belong to it. So it's a left continuous T-norm. If you look at the dual, 1 minus x dual of it, this is what you have. This blue is the boundary of the region where it takes the value 1. And it is clear these ragged edges don't belong to this region. That means the boundary does not belong here. Which means for decreasing sequences, it is true. And hence, it's a right continuous T-conorm. The dual of left continuity will apply here. Finally, all the concepts that we have discussed can be generalized based on duality. For example, you take an element A and fix a T-conorm S, idempotence remains the same. Nilpotence means if you take an A and operate it on itself some finitely many times with respect to S, it should reach 1. Zero divisor means here an A should have a B such that S of AB is 1. This might sound like a misnomer, zero divisor, but it is going to 1. Remember, 1 is the annihilator for the T-conorm. So in that sense, it's the zero element, and so this is a zero divisor. Finally, Archimedeanness. Once again, if you take two elements and apply a T-conorm, it is going to increase, becomes bigger than the argument that you consider, which means Archimedeanness is also defined accordingly. You take an x for some n, it should be such that if you operate x on itself n times with respect to s, then that should be bigger than y. So similarly, almost every concept can be generalized based on duality. Once again, we will look at specific properties when the context warrants. Finally, in this lecture, what we have seen is a generalization of a pseudo-complementation, which is what we call a natural negation of a T-norm from a T-norm. So it's natural negation of a T-norm. From there, we generalize what could be a fuzzy negation. Just the boundary and the monotonicity conditions were imposed on it. Other properties were desirable. Finally, we looked at one particular generalization of fuzzy disjunction, which we call the T-conorms, and we saw them as n-duals of T-norms. What next? So, in this week, we have discussed only about conjunctions, largely about conjunctions, and their generalization, and all the algebraic analytic aspects related to them. We have also seen about fuzzy negation and T-conorms, which are generalization of complementation and disjunction. Next, we look at fuzzy implications, which are one of the most important operations from the point of view of logic and hence from the point of view of reason. In the next week, we'll look at fuzzy implications almost along the same lines as we have seen T-norms. Once again, for the topics covered in this lecture, a very good resource is the book by Clement Messier-Park titled Triangular Norms. Thank you once again for joining me in this lecture and hope to see you soon in the next lecture. Thank you.